delta greater than 0, such that x of t exists, or t equals the set 0 to delta. This is kind of a very limited result, because delta could be much smaller than t1. So it's not a very strong result. So we have this requirement that basically the derivative should be finite within a certain area and for a certain time. But even if that derivative is finite, kind of, we know it's going to be derivative is going to be finite kind of a long time into the future. Even if that's the case, the solution might only exist for a very short amount of time.
You're live now.
Excellent, thank you. So it's not kind of a very strong result for existence. So we don't have a very good guarantee of kind of a solution that it exists. So it's a little bit risky here that a solution might not exist. So, well, you know, if your integrator, if you're doing a nonlinear system and your integrator blows up, maybe you're integrating it correctly, but maybe there's actually no solution for this nonlinear system. So there's, you might have to analyze it a bit more. You might actually be doing the integration correctly. There's just no solution, so your integrator blows up to infinity. So you got to be careful. But we'll try to deal with kind of well-behaved systems in this course for the most part. Now, in terms of global existence and uniqueness, you basically have to have a global Lipschitz condition, which is a little hard to find in real systems. So this was a local Lipschitz condition, saying the derivative was finite in some area for some amount of time. But if you have global existence and uniqueness, so if, in addition to the above, we have assumptions the norm of x1, the norm of f of x1 and t minus the norm of x2 and t is less than or equal to some constant L times the norm of x1 minus x2. And we have f at x0, the initial condition, and t. The norm of that is less than delta. Delta also being a positive constant. And this time it's for all x1 and x2. In Rn. And for all t. And still talk about a finite interval for the time. Then x1 of t has a unique solution in 0 to t1. So this time we can, it meets these conditions from 0 to t1. Now it actually exists all the way up to time t1. So that's a much better condition. But this is actually kind of a hard condition to meet. So something that's globally Lipschitz is kind of rare. So like sine x or cos x is globally Lipschitz. So you get x dot equals sine x, it would definitely have global existence. But if you have something simple as x squared goes off to infinity as x goes to infinity. So it doesn't meet this criteria of being globally Lipschitz everywhere, because the derivative does go up to infinity. So even something as simple as x squared doesn't have global existence of a solution. it's just something to be aware of with nonlinear systems, is they're quite different than linear systems. You simulated a linear system and it blew up, you knew you were doing something wrong, absolutely, because it should be well behaved. Nonlinear systems, not necessarily the case. So, I mean, I guess a real practical example would be like talking about controlling robots in this course. Well, you know, if you get the robot moving too fast, at some point the robot moving too fast is going to blow up the integrator. You're not going to get a good numerical solution anymore. Your solution will go crazy. So it's just kind of a practical aspect to it. Okay. So let's write down some of the stuff I just said out loud before about non-autonomous systems. So normally we deal with non-autonomous systems in nonlinear control. Because if it was autonomous, we would probably design a linear control based on the linearized system. So for example, let's look at the pendulum. And suppose we want to follow a trajectory. Because if I wanted the pendulum to just stay in one place, I would almost certainly linearize pendulum dynamics and design a linear control. But it's when we get into a time-varying trajectory that I actually have an incentive to switch over to using a non-linear control. So suppose this is my desired trajectory, and I define my states now to be errors. So I have an error in position for x1, and x2 becomes an error in velocity, rather than being position and velocity as we saw before. And the state space model is x1 dot equals theta 1 dot minus theta desired dot. X2 dot equals theta double dot minus theta desired double dot. So x1 dot equals x2. X2 dot equals minus k1 psi theta minus k2 theta dot plus k3u minus theta double dot desired. So x1 dot equals x2. X2 dot equals minus k1 sine x1 plus theta desired minus k2 x2 plus theta dot desired plus k3u minus theta double dot desired. So now when I sub that desired trajectory in, I'm going to have t appear here explicitly. So since t appears explicitly, this is a non-autonomous system. In other words, it's in the form x dot equals f of x and t. So you can see that, the system itself doesn't have to depend on time. I don't have to have a changing friction in the pendulum. I don't have to have a mass that's evaporating. I don't have to have a length of the pendulum that's getting longer or something like that. All those things could possibly happen and be not autonomous, but that's not very realistic in actual life. But following a desired trajectory is a very realistic situation. So that's what I want you to do when you do your project. I'm giving it, like I said, I'm setting up this code now, or I'm giving you this code for the rigid robot, and I'm going to get you to modify it for a flexible joint robot, which I think will be a good exercise, but at least you get a nice starting point. But I will give you code for the robot that's following a square trajectory. So it's going to be like a planar robot, and it's just going to trace out a square. So you can keep that if you want, or you can do like a more elaborate trajectory. But you definitely want to have some trajectory following in your simulation, for sure, because that's the real need for nonlinear control in a robot. If your robot just needed to go to one particular place and be there really accurately, you could just use PID control to do that. But it's when you need accurate movements and motions of the robot that you have to go to the nonlinear techniques. Now we're going to get into Lyapunov theory. So I'm just going to make a note. I mentioned this before, but these nonlinear systems can have more than one equilibrium point. We always talk about stability of an equilibrium point, not the system. So that's different than a linear system. In a linear system, you say stable or not stable. But a pendulum, it wouldn't make sense to say the pendulum is stable, because the pendulum pointing straight down is stable, the pendulum pointing straight up is unstable. So it's the equilibrium point that's important. In terms of who Lyapunov was, he's like a Russian guy. The Russians were very highly into control, nonlinear control, basically because advanced control systems are a good way to get your system working a lot better without actually improving the hardware. So the Russians and the Western world had very different approaches to control systems. So in North America and Europe, traditionally people have put a lot of effort into building really expensive hardware, so you didn't have to have advanced control systems. Whereas Russians had more, might I say, primitive hardware. Hopefully there's not any Russians in the room. More primitive hardware, and they put a lot more effort into making their control systems advanced to make up for the lack of performance of their hardware. So there's kind of this very Russian tradition, especially in nonlinear control, that they're kind of inherited. I'll give you a good example. I was in on a defense of a PhD candidacy proposal exam, and my student was proposing wastewater treatment control. So when the wastewater comes in a rainstorm or a flood or something, a storm, the whole plant gets diluted. So the idea is to have a really advanced control system so it doesn't pollute even during rainstorms, because with current technology, it does actually exceed environmental standards during rainstorms, like what's going into the river. And so one of the professors stuck up their head and said, why don't you just build a separate set of pipes for the wastewater from the toilets and the rainwater from the streets. Well, that's a good solution, but it's like a $10 billion solution, right? Updating the software with a new control system, that's a much cheaper solution. So it's just the way people think about things in North America. It's like, well, why don't you spend $10 billion so you don't need a better control system? I don't know. So the equilibrium point, x equals 0, of x dot equals f of x of t, with x of t naught equals x naught, is stable. So this is the definition of what stable means at time t naught, if given epsilon greater than 0, there exists delta that's a function of epsilon to t naught greater than 0, such that if x naught stays within a ball radius delta, that implies that the solution x of t will remain within a ball of radius epsilon. So remember how I said this works with these mathematical definitions. Epsilon is like a really small number. Think of it as a dialogue. Epsilon is a really small number that you're thinking of. So you're thinking of an epsilon that's like 0.001. So you're challenging it with like a small epsilon. You want to make sure the trajectory always stays within 0.001. And then so I go and calculate a delta that's based on your epsilon, and in this case also the initial time. And I do my little calculations, and I come back and I say, aha, I found a delta such that if we start within my ball of radius delta, I will indeed meet your challenge and stay within your ball of radius epsilon. And then you come back and you say, well, what about epsilon was 0.00001? Then I have to go recalculate another delta. And it turns out, no matter how small you make your epsilon, I can always calculate the ball of radius delta such that I'll stay within your epsilon, so I can always meet your challenge, no matter how small your imagination. No matter how small you manage to make epsilon. Okay? That's just the way these formal mathematical definitions work. So we'll get into some theorems where we'll see we don't actually have to work with these definitions on a daily basis, but we should keep them in mind. Anyone want to guess what happens when it doesn't? We're going to get into definitions where we don't have to doesn't have to depend on T naught. Does anyone remember from last time what kind of adjective we're going to use when something's not going to depend on T naught anymore? Remember what the adjective was in the last lecture? So if it doesn't depend on T naught, it'll be uniformly stable. So that whenever we see the adjective uniformly in this course, sorry, did I erase that on you? No. Whenever you see the adjective uniformly in this course, it's always because you're eliminating that dependence on T naught in the definition. So another definition is that it is, the equilibrium point is convergent at T naught if there exists delta that's a function of T naught greater than 0 such that the initial condition x naught being within a ball of radius delta implies that the limit as t goes to infinity of x of t is equal to 0. So in this case, I kind of don't know the transient behavior only know like what's happening as time goes to infinity. So I have x naught, and it can go out a really long way, the trajectory, and then, but eventually it'll come back in to this ball of radius delta. So it's not like it's going to infinity, but I just don't have any bound on how far it might go. So it could go a very long way. I have actually no ability to put a bound on that whatsoever. So it obviously can't go all the way to infinity because then we can never actually take it back. Which is part of the definition. So the definition, it is asymptotically stable if it is stable and convergent. So asymptotic stability is kind of what usually kind of aiming for in a control system, because if something is stable, it's not exactly like a high performance system. So probably people wouldn't be very happy with the performance of your controller if it was merely stable. So it's not kind of a high performance kind of thing you'd like to, you know, if you're tracking a trajectory or something. Whereas asymptotically stable, that means you're actually, you know, you're going to zero. So remember we said just saw the last pendulum example. So from now on, when we see something like x, we're probably thinking in terms of like this being an error, really, right? Just like in the pendulum example, we were tracking a trajectory x1 to x2. We're actually position errors and velocity errors. So from now on, we'll probably think of this in our heads whenever we see stuff like this. You know, it's really playing the error goes to zero when we're doing a control system. So that's kind of obviously what you want in a control system, is your error goes to zero. But it's not as strong as a linear system, because in a linear system, when a linear system is stable, it's exponentially stable, because it actually follows an exponential into zero. So asymptotically stable is not as strong as exponential stability that you find in linear systems, but it's usually kind of the best you can do as a nonlinear system. It is uniformly stable if it is stable and delta used in stable definition does not depend on T naught. So you have a delta equals delta of epsilon. So if I'm calculating delta, radius delta, to stay within your ball of radius epsilon, I no longer have to take the time, starting time, into account when I do my calculation. Definition, it is uniformly convergent if it is convergent and delta used in the definition does not depend on T naught, i.e. talking about a constant delta in that definition, in the convergent definition.
1 sec for that one.
Okay. That's good, because I'm not done my coffee yet. Okay now?
Yep.
So the equilibrium point is uniformly asymptotically stable. If it is uniformly stable and uniformly convergent. So what we want is we want a nice theorem, because to prove that a control system is uniformly asymptotically stable, we don't want to have to play this epsilon delta game. That would be really annoying. It's fun the first time, but it's really annoying after that. So what we want is a really nice theorem that we can use on a daily basis to kind of prove something's uniformly asymptotically stable and bypass these kind of definitions. So that's when we're going to get into these Lyapunov theorems. They're going to help us do this. But before I cover Lyapunov theorems, I have to define what I mean by positive definite functions, because all these theorems will talk about functions being positive definite, so I actually have to define my term for that first before I can get into the useful theorems. Given b of x and t, that maps some subset of the real numbers d and r plus into the real numbers. And assuming that 0 is a member of d, that b of x and t is continuous and continuously differentiable. So we probably, I did a definition of continuous last time. That's probably pretty obvious what continuous is. Anyone remember how you check for something is continuously differentiable? How do you check that? In a practical way. It's the same thing as, remember from last lecture?
Was it you can take the derivative?
Yeah, well, close. Which kind of derivative? Remember, this is talking about r in here. Talking about x being a vector, right? So all the partial derivatives. So all the partial derivatives have to exist. Okay. In other words, you can find like a gradient. If the partial derivatives exist, you can always find the gradient of a function, right? I remember what gradient is. Fastest way downhill. So anyway, all the partial derivatives have to exist. Okay, so now I have a definition. So v of x and t is positive semi-definite. Indeed, if v of 0 and t is equal to 0 for all t, v of x and t is greater than or equal to 0 for all x that are not equal to 0, and x and d for all t. example here, b equals sine x plus 1. So b equals 0 and x equals minus pi over 2. So the first thing I probably do is I want to talk about b of 0 being 0. So don't make the mistake of looking at this and saying, well, b is 0 and x equals negative pi over 2, so it can't possibly fit into this definition. Remember, if you see something like this, it's kind of this trivial coordinate change. You know, when I write these definitions and theorems down, I'm always assuming that I've made the coordinate change already, so that things are 0 at 0. So for this system, you just have to make the change of coordinates first, and then it'll look like that. So first do change of coordinates. So we do have b of 0, b equals 0 at 0. So I have to do x minus negative pi over 2 for my z, my new coordinate. Sine z minus pi over 2 plus 1 has b of 0, b equals 0 at z equals 0. Okay, so it's just a trivial coordinate change to meet this first criteria. So like I said, if you're doing a project, obviously you have to do that first, but anytime I write something on the board in kind of a general sense, I'm assuming that's already been done. So I'm just assuming it's kind of trivial. So then if I was to draw this thing, B is positive, definite, and I haven't even defined what I meant by positive definite yet, so I'll do that next. I'm kind of starting with the example here before I do the definition in this case. Positive definite between negative pi over 2 and pi over 2